Hello and welcome to my next tutorial about PrePoMax. This time I will show you how to simulate snap-through buckling of a spherical shell. So let's create a new model first with the default settings, and now I will import the geometry. As you can see, the geometry in this case is very simple, it's just this dome shape. You can see some warning here, but it's nothing to worry about. So let's just apply the mesh. I will set meshing parameters, and for the maximum element size I will set 5 millimeters, and I will leave the rest with the default settings. So I can click OK and create the mesh. Now the mesh is created, so I can proceed to the analysis setup. So let's define the material first. This will be our usual steel material, and I will just specify properties for this one. And I also need to define a section. Of course, this will be shell section because it's a surface geometry. And for the thickness, I will specify 8 millimeters. And I will select the part here, so I will apply the thickness to the section to the part. And now I can proceed to the rest of the simulation setup. Actually, in this case, it's quite simple. I only need to define the step, which is a static step. I will change the solver to Paradiso, the fastest one, and what's super important and necessary here, I need to enable geometric nonlinearity to be able to simulate this nonlinear snap-through buckling. Then I will also adjust the incrementation settings. Just in case, I will increase the maximum number of increments, but I will also reduce the initial increment size and maximum increment size to make sure that I can obtain accurate results. That's everything I need to set for this. And now let's proceed to boundary conditions and loads and the rest of the setup. So let's apply a boundary condition first. The dome will be fixed on this edge here, so I'll select the edge and fixed boundary condition, and that's it. And now I just need to apply the pressure load, so I will select uniform pressure, surface here, and the value is 5 megapascals. So this is our load case. And now I just need to make additional settings for outputs. First of all, I will go to element output here, and I will change it to 2D. This is something I wouldn't normally do for shells. I would keep the default, which is 3D. To obtain proper stress results, but in this case it will be easier to visualize the snap-through buckling with this 2D representation, so I will make this exception and set it to 2D. And now I also need to set the history output. I will select node output, pick this node, there's vertex right here, and leave the setting to write the displacements. Alright, so let's confirm this. And now I can pretty much submit the analysis and wait for the results. The analysis is completed now, so let's check the results. Okay, let's take a closer look at the results. First of all, you can see the typical shape for snap-through, so let's have a look from this side. And now if we check various increments, you can see let's just switch the scale factor, and now if we go through, maybe I can also hide the mesh, and now if you go through different increments, you can see how the snap-through occurs suddenly at a specific point in the analysis. So you can notice the behavior occurring here, and it's clearly a snap-through behavior. When looking from this side, it's visible that at some point there's a sudden change of the state of the dome, and you can see how it behaves on this animation. So this is the first thing, the deformed shape and animation of the snap-through behavior. And now the most important part is to analyze the equilibrium path. So let's expand the results here, and what we saved before for the node in the middle, we saved the displacements in various directions, but we are interested in, of course, in the vertical displacement, so we can open this. And now, of course, we should create a plot of displacement compared with applied load. So we could use those values here. We could just copy them and paste to a spreadsheet, but in my case I already did that, and I can show you the results. Of course, we can have a look at the extreme values, and you can compare them with what I have in the spreadsheet from a previous run of the same case. So you can see that we have the results with the plot available here. I just multiplied the time increment by the value of the pressure to have the pressure at each point of the analysis, and then I took the absolute value of the displacement and obtained this plot right here. And this plot is basically a typical behavior observed in snap-through analysis under load control, because what's important here is that CalculiX doesn't have the Riggs or arc length solver, so you won't get the classic shape for snap-through behavior, and instead you get something like this, that at some point is a straight line, and then you jump to another configuration. So that's what happens when you have just load control without arc length solver. But we can clearly see the snap-through behavior here. And now, of course, we are also interested in the pressure at the value at which this behavior occurs. And for that, as always, I have some analytical solution. And in this case, actually, I have multiple solutions obtained from different references. So we can see that for given thickness and radius of the dome, and of course the material properties, I have different formulas from different publications. And if you look at them, you can see that there are some clear differences. So in this case, it's really not easy to predict the pressure in the critical pressure in the case of snap-through buckling of shells. So we can see that various publications differ, and there are some additional notes here. For example, for the first one obtained from Timoshenko's book, you can see that this classic formula can actually over-predict the critical pressure 2 to 4 times. So when looking at this value, you need to remember that in actual experimental studies it was proved to be much lower. Then we have the second formula from another reference. The value here is lower, and then we have yet another study with this value, but then in that study it was also mentioned that the actual value can be like this. So if you compare what we have here, you can see that snap-through occurs somewhere around this critical point. You can see that the value is between 2 and 3, it's above 2. You can see that if we compare it with what we have here, there's no exact solution for that. You can notice that those formulas either overpredict or underpredict critical pressure, but some are pretty close, and you can see that we are always, let's say, pretty close to the actual pressure, critical pressure for this structure. So if you compare the different results here and have a look at what we've noticed here, you can see that we aren't very accurate with those predictions, but some of the formulas, let's say, for example, this one, taking into account the actual values or the correction with respect to experimental studies, or maybe also the last formula can be quite close to the actual critical load we obtained from the simulation. And also we need to remember that there were no imperfections here. It was perfect geometry, and those shell structures are really tricky when it comes to buckling, nonlinear buckling analysis, and it's really hard to predict their critical loads, especially analytically, but often even with the use of simulations, but especially if you want to use such simple closed form solutions, formulas like this, you need to be aware of the discrepancies that may occur in such cases. But still, you can have some rough prediction using the values obtained with different formulas. Unfortunately, they vary quite a lot, but they give you some understanding of what you can expect. And then in the simulation, you can see some additional predictions And then of course it would be ideal to carry out some experimental studies to obtain even more accurate results, but this is really a tricky topic when it comes to nonlinear buckling of shell structures. Alright, that's it for this PrePoMax tutorial. Thank you very much for your attention. As always, feel free to ask any questions and suggest topics for future tutorials in the comments. Have a nice day and see you in the next video.